Coffee. Easily. Throwing things. I got it. I'll keep those. All right. So we're not needing to do any solving on this one. We're just matching equivalent expressions. So think of it as if we were to switch these to and from exponential form. This is very much based on that BPA log BAP stuff. So B P equals A, and that's equivalent to y log base B of A equals C. This kind of stuff. So what do we think? What pieces are going to match up here?
A and 4.
A and 4. Yep, I'm with you because this is our log base E to the 5x, or of 5x equals 7. So if we switch that around, we have base E power 7 argument of 5x. So that is exactly what number 4 is. So what are the ones we see that match? B and 1. Boop. B and 1. C and 3.
D and 2.
And then D and 2. Okay, so we will have problems like this that show up every now and then because they let us practice this and pay attention to those tiny details. So make sure we know this. I know I've said it repeatedly over the last week, but this is something that we've been struggling with. So please focus on this. Okay. So short bell work today. We've had some doozies lately, so.
We don't get that on the test, do we?
What do you mean? Oh, this part. Nope. You have to know that. Keep saying Band-Aid, knee-high on the silver shelf. Yes. Variety. Those colors. Different options to choose from. All right. So I want us to do one more little solving one before we go into our why the heck do we even have these? Oh my gosh, why? Portion of this. Which I know is going to be everybody's super most favorite thing. So let's look at page 12 real quick.
Oh God, we're doing word problems now? Oh God.
I mean, they're printed in the packet. Because I have people that ask me that very regularly for Band-Aids. Because I'm really far from the nurse. And they don't want to have to walk all the way up to the nurse for Band-Aids.
Like something as simple as a Band-Aid.
Yeah, it's like a 4-minute walk.
They should start having all classrooms should have a box of Band-Aids or something.
That would require them to have money to spend on that.
That is true.
I don't even get paper towels or tissues. That's why we have the roll of toilet paper over there.
Yeah.
All right, so let's look at number 5 on page 12. I know it feels really random choice on that page, but you know what? I liked it kind of best-ish. What can we do here to try and solve this? I want to figure out what P is. That's my variable. What should we start with?
My gut is telling me subtract 2, but then I also want to get rid of the ln.
In order to get rid of that ln, we'll need to switch it to its exponential form, which means I need that log all by itself first. So agreed that both of those things are goals we need to have, but we can only do one of them at a time. Thank you. So I want to eventually switch this to exponential form, but that means I need to have my log and its argument all by themselves. So we got to get this bit by itself. So what are we going to do with that -2 to get rid of it? That -2? Add 2. We need to add 2 to both sides. And that's going to give us 2 ln of this 7p minus 5 equals -6. Now what can we do? With the number out in front, we can't put it in exponential form quite yet. Say it again. You could move the coefficient up to become a power. That is going to make extra work, though. Because if you do that, then we'd have to wind up squaring this and solving it. It's going to be gross. So think of this, instead of being as our power, as 2 times. What can I do to get rid of a 2 times? Divide. So we can go ahead and divide this piece by 2. That gets rid of that coefficient. So now we have our ln, that was the wrong color, ln of 7p minus 5 equals -6 divided by 2 gives us -3. Now we can put it into exponential form. What is our base? E. What's our power? -3. And what is the argument? 7p minus 5. E to the -3 is a number. It's a gross number, but it's just a number. So we're still trying to get p all by itself. What do we need to do to get p by itself here? Add the 5. So I'm going to add 5 to this side, which means I also need to add 5 to this side. So we're going to have our e to the -3 plus 5 equals 7p. Or you can put 5 plus e to the -3. That's also fine. Oh. The cap of my pop socket just popped all the way off. And then we're going to divide the whole thing by 7. Yeah. It's been trying to do that for ages. To be fair, I'm not entirely sure this one is a name brand pop socket. But it does that. There we go. Oops, there we go. All right. So we divide everything by 7 because that's going to make that 7 cancel out. So this guy divides by 7. So we have that p equals the fraction that has our e to the -3 plus 5 over 7. And just like we had when we were doing this with our change of base formula, where we got an exact answer and a decimal approximation, here again we have an exact answer. But if I wanted to know how many pineapples that is, so we need to get a decimal approximation as well. So we're going to type this thing in the calculator, which means that we should open the calculator. It's going to be really important that you guys have practiced at least something on the calculator using this, because there's only so much information I can give you when we're, doing a test. So make sure you know how to use the calculators to do these things. The number of us that have the sheer confidence of going into a test having never done the problem is astounding. All right. Ooh, tiny calculator. All the way back. There we go. Ooh. There we go. So to type that into the calculator, that's when we're going to put our fraction in, that third button down in the second column. And to get to E, we have the second button, and then we hit the ln button. That gives us our E, and it kicks us up into the exponent where we can put in that -3. Come down to the main line and we'll put in that plus 5. And we have our denominator of 7. So make sure it looks just like how you have it on the paper, that we have our e to the minus 3 and then plus 5, or you could do 5 plus e to the minus 3 all over 7. And we get 0.721398, blah, 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 blah. We can take 2 decimal places here because I don't think it says.
Yeah, it doesn't say.
Doesn't say. So we'll take those 2. 0.72. So our decimal approximation for P approximately equals 0.72. So we just hadn't done one where we had ln and we were solving for an exact with e in it. We'd done them with ln's in them, but not with e's in them. So I wanted to make sure we saw it both directions. Questions on this one? Because the next thing we're going to do is we're going to start to look and see why the heck we even have these logarithms. What do these kind of problems solve? And all that jazz.
Ew.
So we're going to start looking at what we're calling the applications of logarithms, which means story problems. But luckily, as it is a packet, they are printed there for you. No writing needed. Oh, snap. You're welcome. So this is the very first one on the next page. It does start with number 7 for reasons. The previous one was number 6, but, you know, it's still a choice. The numbering in the packet is a little chaotic, but that's okay. So we've got here that the magnitude of an earthquake, M, releases energy, G, measured in joules. It's a unit, it's not a huge thing. That is modeled by this equation. So we're straight up given an equation. This is the guy we're looking at here. They say an earthquake in the Pacific Ocean had a magnitude of 7.9. And we want to know how much energy this released. So this 7.9 is going to be for which letter? M. This tells us it's a magnitude. That means we're going to substitute that in for M. So in our equation that we're given, they're saying what happens if M is 7.9? So let's substitute that in. So we're going to have our 7.9 that equals our 3.12 ln of G plus 2.45. And we're trying to solve this for G. That's what we're asked to do. They want to know how much energy. The energy is the G piece. So we are trying to get this G by itself. So what can we do to get G by itself here? Subtract the 2.45. So we need to minus our 2.45 from both sides. Typing that in the calculator, we get
5.45.
Yep, 5.45 equals our 3.12 ln of G. Still working to get that G by itself. What can we do next?
5 to 3.12.
As I say, I heard 2 different things at the same time, and my brain could not process either one sufficiently. Say them again, because I know we had 2 ideas.
Divide by 3.
Divide by 3.12 is an idea? What was our other idea? Both great ideas. So think about what's happening between our 3.12 and the ln. If we don't have a signal written here, what does this mean? Multiply. So how do I get rid of it? Divide. Yeah. So since they're being multiplied, we need to divide this side by 3.12. That's going to make those guys cancel out. That's what we want. We would really like that to just have the G over there. So I need this 3.12 to leave. So yes, it's gross. We can do this. 5.45 divided by 3.12. Yeah, we have 1.7.
I would round up to 5.
So yeah, 7.468, 7.5. However we want to do it. Equals our ln of g. Now what can we do? We can't divide by ln. That would be like saying I'm trying to divide by plus. Ln's an operation. We could put it in exponential form. Yeah, think of ln and log more like the division symbol or a plus. They are a tool that lets us move things around. So writing this in exponential form is going to be what? What's our base? E. What's our power?
1.75.
1.75. And our argument
G.
is g. So technically we have an answer. We've got g by itself. We know the exact answer. Exactly. G gets e to the 1.75. How much energy is that?
No,
We have to put it in the calculator because the exact answer, while exacter, is not necessarily practical. So we're going to need to take our e to the 1.75, and we can do that in our beautiful yellow calculators. We get to our e by hitting that green button on the top left and then hitting that ln button since they are so related. And we can put into our exponent that 1.75. We don't have to do anything to it. And we get 5.7546026676, blah, 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 blah. So we get about 5.75. So G approximately equals that 5.75. And they did, in fact, give us a unit in here. For G is joules. Yes, dear?
So when we put in the exponential form, when we make e our base, why do we make e our base because we don't have a code?
Because it's the ln. And what the ln stands for is our log base e of whatever our argument is. We just write that as ln. Kind of like our log base 10 or whatever that argument is. The argument here. That's when we just put log, that common log. So those two have this shorthand. And these are the only two buttons we have on the calculator. It's just our base 10 and our base e. Okay. So now we have all of our solving stuff and we can start on our story stuff. Questions on this first one? Because sometimes we just straight up give you the equation and it's just about substituting pieces in. So let's look at the next one. We've got that the loudness is measured in decibels. And the formula to give some sort of quantification for that is this guy right here, this dB equals 10 log of I, where I is how many times more intense the sound is above this threshold. It's a weird calculation. Yes, dear. Yes, the marriage passed. So we're given this equation, and then we have two questions. Mine are very close together. Yours have significantly more space to write. So we want to know the decibel rating. We want to find the dB of a cat's purr. That's 316. So think about that 316. Where is that going to substitute into? It's been years since I listened to them, but I was not consuming music when Kiss was first popular. I don't know that I was even born when it was first popular. Yeah, my sister was. I was very much more of the Backstreet Boys and synth type. That was my age. dB, which is 1 unit, decibels is 1 unit, one variable there. What is the 316 going to go in place of? The I. So they're telling us that to get the decibels, we're going to have 10 times log of 316. So how can I figure out what that is as far as like a measurement, a number? We can put that sucker in the calculator. We don't even have to do anything to it. Those are all buttons on the calculator. 10 log of 316. We get 10 times our log of 316.
And it says to round to the nearest whole number.
Yep, nearest whole number. So what are we going to have? 25. So the cat's purr is registering at 25 decibels.
Did you know that tigers actually chuff?
They do also purr, because I watch a lady who owns a big cat rescue, and they do purr, but they do also chuff. I had a cat that used to like bark like that.
They chuff more than they purr.
Yes, more frequently.
Yeah. They're still adorable.
They have big feet. All right, so then what we're going to do is we're looking at part B here. Separate question, but same equation. They say that prolonged exposure to sounds above 85 decibels can cause hearing damage. So we're wanting to know how many more times in tenths. So what is the I at 85 decibels? So what are we going to substitute this 85 in? The dB part. So a lot of times on these story problems, a big part of it is figuring out where to put in our information. So we're going to have that our 85 equals 10 log of I. And we want to find out what I is.
Divide by 10.
Divide both sides by 10. We get that 8.5 equals log of I. And I'm right at the bottom here. I don't like the spacing on this one. What could I do next? Exponential form. How are we going to do that?
It's a common log.
It's a common log.
10.
So our base is 10. What's our power?
8.5.
8.5. And it's going to equal
I.
I. So how can we figure out what I is? Into the calculator.
Ooh, big number.
10 to the power of 8.5. What do we get? You can go individual digit as you go.
3, 1, 6, 2, 2, 7, 7, 6, 6.
316,227,766 times louder. So think of a cat's purr being volume 316. When you're going to get damage is when we're at volume 316 million. So that's a lot louder. But that's where these kinds of problems come from. They come from stories a lot more like this. The super complicated equations are much more the mathy side, and the stories are much more of the simpler style equation solving. So let's look at number 9, because this is where we see these kinds of problems most frequently, is in stories kind of like this one. Because we've got here that the city of Mathville is growing at a 3.5% annual rate. And the current population is 12,500 people. I know, but we've got a growth with a rate and a population. We've seen these. These are from our exponentials chapter. How can we write an equation here? Because they didn't give us one. What's our equation going to look like? Brain isn't braining. I get that. Or do we remember the formula? They typically start with an A. For sometimes that helps.
There's multiple
There are multiple on there.
Would it be A equals P plus 1 plus or minus R to T? Is that the one we're looking for?
Mm-hmm. Because we are not compounding it, this is the equation we use. If it was like a compound interest problem, that's when we have the other pieces with the n in them. For the most part, we're going to look at these kinds of equations. Or, like, typically we'll have this one, or we'll have, like, the PERT. We might have that one come up, too. So, it's open. Is it back? It's back. What pieces do we have in here? What are we going to substitute in? The 3.5 is the what part?
The rate.
The rate. How do we put it in there, though? Do we put it as 3.5? We moved the decimal point how many times? 2 times. So it's going to be what? So we'll have our 0.035. Hang on a second. What else do we know?
That's like our base number, so that would be 12,000.
It'd be the 12,000. It usually stands for principal or population. It's the starting amount. It's what we start with. So we have a little bit of information here. If we don't look at question A, we can fill in a few bits. We've got that the amount of people we're talking about is our 12,500. We've got our 1. Are we going to use the plus or are we going to use the minus? The plus, because we see that it is growing at that 0.035 to the t. So the first question we're asked is how many people are going to be there in 5 years? How do we figure that out? Put 5 in for t. A is actually 100% a exponential question. It's what we did in the last chapter. So we're going to take our 12,500 times R1 plus 0.035, so we have our 1.035, substituting into the 5. So how many people are going to be in this town? In Mathville?
1.
Say it louder. Yep, so 14,840. What are we rounding to, though, because it's a living creature?
I would go 6,
Because
5 and above go
right.
up.
We round to the nearest whole unit because it's people. Don't toss 0.4 people into the town. It will affect your population. People will run. If you start tossing random limbs into the center of town square. If you have 0.4 people tossed into town, that to me that's 2 legs. You toss 2 legs in. It's probably gonna affect the number of people in town. If you start tossing random lids into town square. All right. So that's very much what we did in the last chapter. Part B is really how this works for our log stuff. Because now they're saying how many years. So we're asked to figure out the t to get a town of 20,000. So we're going back to our equation. And instead of substituting in for t, now we're substituting in for a. So we want to know 20,000 equals our 12,500 1.035 to the t. And we need to find t. That's what we're trying to find. How can we do that? We need to move the 12,000, but we can't subtract it because there's not a plus here. Divide, because they're being multiplied right here. So we need to divide this piece. So we're going to divide both sides by 12,500 because then that guy cancels out over here. So that's going to give us our 20,000 divided by 12,500 gives us 1.6 equals our 1.035 to the t. What can we do here? Say, yeah, we need to switch its form. It is currently in exponential form, so we need it to be in log form. So how would we write this as a log? It's going to be log what base? 1.035, which is kind of icky for a base, but whatevs. What's our argument? 1.6. And it's going to equal our power, which is t. We're trying to get t. We're trying to find t by itself. So technically, I have t by itself. How many years is that? How can we find out how many years it is? Put it in the calculator. But can I put it in the calculator just like this?
No.
What do we need to do?
Change of base.
Change a base. How are we going to do that?
Log 1.6 over log of 1.
Yes.
Right.
Log of 1.6 over log of 1.035. I will fill in the petit. Because we're not going to be at the petit. I'm on TikTok way too much, y'all. Just saying. We have to change the base because I can't actually type this sucker in the calculator as it is. Because we don't have any way to type a base of 1.035 in the calculator. The only logs we have on the calculator are the common log up here and the natural log here. We don't have log with blank base. Most calculators don't have that option. There are some that do, but there are not many. So we can do log with our numbers, with our 1.6 over our log of 1.035. Or you can do it with ln. It genuinely does not matter which one you do as long as we don't mix and match.
Now would we round to the nearest whole number for this one, even though it's years?
We can leave decimal places on years. If it's living creatures, we leave no decimal places because we are ethical. If it is money, we do 2 decimal places. Everything else we should have told you where to round, but we didn't in this case. So we'll take 2 decimal places on this one. So we're going to have our 13.66 years. So it would take 13 and a little more than a half years for this town to grow up to 20,000 people. But being able to take these exponential functions that we've written equations for, oh snap, we've done these, and being able to solve for t, figuring out how much time until, oh, my bank account doubles, how much time until I owe $100,000 in credit card debt, you know, that kind of stuff. Using logs is how we can figure out how much time until. Or, in cases of PERT, I could even go, what do I need my interest rate to be for this to happen? So it lets us solve for that exponent in a whole lot easier ways. Okay, we are going to continue practicing with our story problems tomorrow. But I'm not gonna make us keep going because we only have like 5 minutes left. Boop. Okay, so 8.4, which is our homework that has the story problems. I'm gonna go ahead and make it due Monday instead because we're gonna keep doing story problems tomorrow. So it's not due tomorrow, it's gonna be due Monday, which I can't remember the day for, so I'm just gonna put that there. Okay, so you guys have about 5 minutes right now. So if you got questions on what you've done so far on 8.4 or on anything earlier, totally cool. You just need some time to work on stuff, ask questions, all that jazz. Huh? My collection of memes is vast and relevant. I know. I'm like, it's a good one. I was like, I haven't gotten to use very many of the memes this year, but I decided to work a lot of them in. I used to put a new one up every day on the Canvas page, but nobody goes on Canvas anymore, so I stopped wasting my energy.